Good afternoon, class. We are looking at exam 3 review, covering chapter 3 differentiation rules and chapter 4 application of differentiation. Exam 3 covers from 3.9 to 3.11 and 4.1 to 4.5. There's the second part, 3.10, linear approximation and differentials, 3.11, hyperbolic functions. Differentials and linear approximation. For y equals f of x, we define dx called the differential of x by dx equals delta x. In other words, just the run, this distance of bp or delta x or dx. And dy called the differential of y by dy equals f prime of x dx. So we have a curve. We have 2 points P and Q. As we move from P to Q, the run delta x dx bp, the rise is delta y, and there is a tangent line. The rise along the tangent line is dy, or this distance AB. The rise along the curve is delta y or pq. So f prime of x or dy dx, you treat that as a fraction, the cross product gives you dy equals f prime of x dx. As I mentioned, delta y, as we go from P to Q, the rise along the curve, delta y represents the rise along the curve, which is this distance of BQ, or this distance of CQ minus dp, this distance, f of x plus delta x, minus this distance, f of x. So as you can see, precisely, delta y is f of x plus delta x minus f of x. We can replace delta y by dy for a function f which is continuous and differentiable function with a small dx. Why would we do that? If delta y is difficult to evaluate, dy, this distance, can approximate delta y this distance. This illustration has blown out of proportion, so you can distinguish between delta y and dy. But these two values must be very close because we are looking at a small delta x or dx. The smaller the two, the closer these two values. Therefore, f prime of x, which is dy dx, can be approximated by delta y over delta x, and delta y would be the product of f prime of x and delta x, or dx. So now, everyone, delta y is f of x plus delta x minus f of x precisely. Moving things around, f of x plus delta x becomes f of x plus delta y. Move this one to the others. We also know that f prime of x is dy dx, and therefore dy is f prime of x dx. Now, if we want to approximate this, f of x plus delta x equals f of x plus dy, which is f prime of x dx. This is called using the differentials. If you look at this point and give it the pairs a comma f of a, you can obviously find the tangent line, which is also known as linearization. Linearization refers to finding the tangent line at some point A. This is the point slope. Y minus y1 equals m times x minus x sub 1. Move the y1 and now replace the m with f prime of A, x sub 1 with A, y sub 1 with f of A, or L of x is f prime of A times x minus A plus f of A. You don't have to memorize any of this stuff. Just use the point slope, find the equation of a tangent line, give it the name L of x, which is the tangent line, known as linearization of a function, meaning at some point the curve and the line become the same, okay, at a very small interval that happens. For y equals x times 4 minus x quantity cubed, find dy. Well, f prime of x or dy dx means differentiate. So we are going to differentiate. To differentiate, we use the product rule. So we need f prime, which is 1, times g, which is 4, minus x cubed. We need g prime f. Now the derivative of this piece is 3 times 4 minus x squared times the derivative of the inside, which is negative 1. Let's repeat. 3. This is the extended power rule. 4 minus x squared times the derivative of the inside, which is negative 1, times f times x. We can simplify this by taking a common factor. You notice 4 minus x is in common. This has exponent 3, this has exponent 2. You go with the smaller of the two. So 4 minus x squared, this piece is in common. So if we use that, this gives us 4 minus x. This gives us 3 and negative 1 on x minus 3x. So the first part gives us 4 minus x. The second part, minus 3x. And so we have 4 minus 4x. Factor the negative 4, put it in front. And that's dy. Now, x is 5, dx, or delta x is 0.2. We want to plug in first, we need to find dy. What is dy, everybody? It's exactly the same thing, times dx. So the same thing that we found times dx results in dy. And that's important to understand. Let's plug in. So what happens when we plug in? Negative 4 remains. 4 minus 5 times 5 minus 1 times 0.2. And this is actually easy. This is 1 when you square it remains unchanged. This is 4 times negative 4. Negative 16 times 0.2 is negative 3.2. And now we want to find delta y. And delta y is precisely f of x plus delta x minus f of x. And that means f of 5.2 minus f of 5. So plug in 5.2 here, plugging 5 here, you have to go back to the original one and evaluate it. And it gives you negative 3.64 plus 5 minus negative 8.64 plus 5, which is negative 3.64. So it's pretty straightforward, class. What I want to make a point of is the following. If you look at this number and this number, they are fairly close. They may not be as close as you wanted them to be, but they're fairly close. And they become even closer if delta x becomes smaller and smaller. The smaller the delta x or dx, the closer these two values. Differentiate y equals ln of sine theta. And for the natural log, you flip it over. In the case of ln of g of x, you flip this over, you get 1 over sine theta. And then by the chain rule times the derivative of sine, which is cosine. So the answer is cosine theta over sine theta. And you know that one is cotangent theta. What about this function? So f over g, we are going to use the quotient rule. So y equals e to the power of x over 1 plus x. F prime is e to the power of x times g, the bottom is 1 plus x. Again, the way I differentiate, class, I look at this and I need this. I'm going to write the quotient rule from the memory and use that. And it's a lot faster than writing ddx of this, ddx of that. Minus g prime minus 1 times f e to the power of x over g squared. Put the bottom in a parenthesis and a square. And we're done with calculus. This is e to the power of x. This is e to the power of x, e to the power of x times x. This is minus e to the power of x. These two cancel each other. And the numerator, we put the x in front because that's awkward otherwise. So x e to the power of x over 1 plus x quantity squared. Find the differential of each function. Well, for part A, we found y prime to be cotangent theta. So dy is the same thing times d theta. For part B, we found y prime to be x e to the power of x over 1 plus x squared. So dy is the same thing, times dx. So pretty straightforward, everybody. Use differentials to approximate 51 squared. By the way, you may remember from algebra, if you wanted to do that, you would go with this method, which is 50 squared plus 2 times 50 times 1 plus 1 squared. So you recognize this as 26 over 1 in no time, right? That's one way to use those identities that you get. What is the process? Number one, we need a function that represents this operation. So all you have to do, read 51 what? Squared. So the function that we need, f of x must be x squared. Step two, choose a number x close to 51 for which squaring is easy to compute. And I hope you recognize that number is 50 because when you want to square a number that ends with 0, so you just square the 5 and then 0, there is 1, you make it 2. It's that simple. Everybody knows that. So what is dx or delta x? 50 is the easy number that we are going to work with. And from 50 squared, we want to go to 51 squared. We want to make it larger. So the difference between 51 and 50 is delta x or dx, which is positive 1. And I can't emphasize this enough that it's positive 1, because if I was interested in finding, for example, 48 squared, then I would say 48 minus 50 is negative 2. This would be delta x or dx, okay? Would be negative. So we need to understand. So now we are going to use differential to approximate. So we go back here and we say f of x plus delta x is this, approximation is this. So we're going to go with f of x plus delta x is f of x plus dy, because we are approximating. So what is f of x? We have it is x squared. What is dy? We don't have it yet. We know f prime or dy dx is 2x. Therefore, dy is 2x dx. And so now we have f of x, which is x squared, plus dy, which is 2x dx. So what is x? 50. What is dx or delta x? 1. Plug in. So 51 squared means f of 51 means f of 50 plus 1. Replace the x with 50. replace the dx with 1. As you can see, this is 100, this is 2500. $2,600 is the answer, and obviously extremely close to the actual answer. And by the way, the reason it's close, because delta x is fairly small to compared to 50, which is the value of x. We are done with this. I want to remind you of what we discussed as far as linearization. This is the second method, ultimately gives you the same result. What does it mean? It means for this function, at this point, find the tangent line. You want to find the tangent line, you need two things. You need a pair. So what's the pair? 50, 2500. You also need the slope. What's the slope? F prime of x is 2x, so f prime, that means m is 2 times x. Okay, so I want you to know how you find the equation of a tangent line. And so that results in the tangent line, which we call it L of x. So let's stick with the point slope. Y minus y1, y minus 2500 equals m 100 times x minus 50. So this is 100x minus 50 at 2 zeros and sub negative 2500 becomes 2500. Add them up, we get 100x minus 2500. Now, if you replace the x with 51, you get 100 times 51 minus 2500, which is exactly the same as this one. These are two different versions of the same process. Differentials versus linearization. Let's look at another example. Use differentials to approximate cube root of 63.5. You go through the same process. Number one, you need a function. What is the function? Just read this. Cube root of something. So cube root of x. Step two. Choose an x to be a number close to 63.5 for which the cube root is easy to compute, something you can do it in your head. $64 because the cube root is 4. We should know this. And so what is dx or delta x? We're going to subtract 64 from 63.5 and it gives you negative 0.5. And this is what I meant in the previous page when I mentioned that. We know the cube root of 64 and we want to find the cube root of 63.5. So this means whatever this answer is, this is close to it, but it's smaller because it's negative 0.5. Okay. On the other hand, just let's make it up. If I wanted to find cube root of 65, I hope you see that dx would be 65. minus 64, which is positive 1, just as an example. All right. Now, so we have approximation. That means we are going to use, this is the exact, we're going to use this one, f of x plus delta x is f of x plus dy. So we have f of x. We don't have dy, we're going to find it. To find it, we're going to change this to x to the power of 1/3. Because we are going to differentiate and find f prime of x. By now, we know 1/3 x to the power of 1/3 minus 1 or negative 2/3. This one goes to the denominator, becomes x to the power of positive 2/3 or 1/3. This 3 remains, cube root of x to the power of 2. So this is f prime. What is dy? The same thing, times dx times dx. So we put the dx times 1 in the numerator. So f of x plus delta x can be approximated by cube root of x, which is f of x, and dx over 3 times cube root of x quantity squared. Please understand, if I put the 2 in or out makes no difference. In other words, cube root of x squared is the same as this one, okay? So I hope you know that. So what we want is cube root of 63.5. So we have those functions, right, everybody? So pretty straightforward. Which is what? F of 63.5, which is what? F of 64 plus dx is negative 0.5. And I write it in this fashion, so clearly we're going to change the x to 64 and dx to negative 0.5. So let's do that. Cube root of 64, it's 4. This is 4. You square it, you get 16 times 3, you get 48. Now, there's a reason I'm changing to a fraction on purpose, because first I want to give you the exact answer. And so negative 0.5 or negative 1/2, see, plus times minus. 1/2 over 48 means 1/2 times 48 means 1/96. So 4 minus 1/96. And if I want to write it as a fraction, I hope you recognize you should be able to do this in your head. This is the fraction 395/96 precisely. This is the approximation using a calculator. Now, if you put that into a calculator, the first 4 are the same. See, 1, 2, 3, 4. And if you want to stop here, you have to change it to 6. If you want to stop here, you have to change it to 6. That's how close it is, because 0.5 is very small compared to 64. Remember, dx is negative 0.5. Negative or positive, in a matter of comparison, you want to see how small it is compared to that. Here's the linearization. Here's the second method I want to look at. So the question is, what is L of x? Well, again, you don't have to memorize any of them. Go back to the basic point slope. You need a pair. X equals 64. What's the pair? 64, comma, 4. What's the slope? You put it here. F prime of x. Remember, if you put 64, you get 4. Square it 16 times 3. It's 48. 1/48. So Put number 64 into this to get the y coordinate, into this to find the slope. Point slope, y minus y1, meaning y minus 4 equals m1 over 48, x minus 64. So you multiply this through and you move the negative 4. So you get 1 over 48 x minus 64 over 48. They're both divisible by 16 4/3. You move the negative 4, make it positive 4. This is negative 4/3 with 4/3 becomes 8/3. Let me erase my work so you can see. So this is L of x. Now, what do we have to do? We have to plug in 63.5 instead of x. And if you do that, you get the same answer as here. If you keep it at 63.5 and as a fraction, you can end up with this precisely. For y equals f of x equals sine x, find dy. So the moment you hear that, ignore that. Find f prime, dy dx, and you know the derivative is cosine. So dy is the same thing times dx. Dy is the same thing times dx. Find its linearization at pi over 6, meaning find the equation of a tangent. That's all. That's all. Find linearization means equation of a tangent line. Just find through the process of y minus y1 equals m times x minus x. So we need a pair and we need this slope. What is the slope? Well, here's f prime of x, plug in cosine of pi over 6. So that's the slope, which is square root of 3 over 2. What is the pair? X comma sine x. What is x? Pi over 6. What is sine of pi over 6? 1/2. So y minus y1, that means y minus 1/2 equals m, that means square root of 3 over 2 times x minus x of 1, that means x minus pi over 6. So we distribute and we move the negative 1/2. So y L of x becomes square root of 3 over 2 times x. Multiplying these two gives us minus square root of 3 pi over 12 plus 1/2. And you keep it as that. This is an exact answer. Leave it be. approximate sine of 31 degrees. As you know, 31 degrees is not a common arc. That's why they're asking for approximation. And we're going to do that. Sine of 31 degrees, we are going to look at it two ways. Number one, sine of 31 degrees is sine of pi over 6 plus pi over 180. Pi over 6 is 30 degrees. F of x plus dx is f of x plus dy, which is f of x sine x plus dy cosine x dx, which means sine of pi over 6 plus cosine of pi over 6 times pi over 180. 1/2 3 over 2 times power 1. At this point, class, you have to pi over 180. You have to put it into a calculator times square root of 3 over 2 plus 1/2, and it gives you about 0.5151. If you put sine of 31 degrees into a calculator, also it gives you a number close. Okay. Here's the second method that we want to look at. Sine of 31 degrees or sine of 31 pi over 180. We are going to replace the x with this. Use linearization. So L of 31 pi over 180. This is the concept of approximation. Approximation through differentials or approximation through linearization. And by the way, they give you the same answer. So you put the square root of 2 over 2 times 31 pi over 180 minus square root of 3 pi over 12 plus 1/2. Now you use a calculator and it should give you the same answer, and it does. One side of a right triangle is known to be 20 centimeters long, and the opposite angle is measured as 30 degrees. With a possible error of plus minus 1 degree, use differentials to estimate the error in computing the length of the hypotenuse. What is the percent error? So you have to, if it's not given to you, you have to draw the setting. Okay. So this is 20. The opposite angle is theta, which is 30 degrees with a possible error of plus minus 1. Use differentials to estimate the error in computing the hypotenuse. What is the hypotenuse? We don't know. We say it's x. So here's the given. Theta is 30 degrees. So we're going to write one leg is 20 centimeters. And again, we do have this drawing because it's opposite the angle. The angle opposite that is 30 degrees. Now, this possible error means plus minus 1 degree. Okay, that's the meaning of plus minus 1 degree. The possible error is referred to as d theta, everybody, which is, of course, plus minus 1 degree or plus minus power 180. And we want to know what? Use the differential to estimate the error in computing the length of the hypotenuse. The error, or dx. So that's another terminology for dx is the error. So we have to relate the quantities in this case. What quantities? 20 and x and theta, and we know sine of theta is 20 over x. Which means you can interchange these two. You can say x is 20 over sine, or 20 times cosecant theta. That has the same meaning. Remember, cosecant is 1 over sine. Either way is fine. So if we go with cosecant now, remember we want dx. That's why we are going to solve for x. Now that we solved for x, we say dx d theta is the right side. We want to differentiate 20 times. Cosecant, the derivative is negative cosecant cotangent. So dx d theta is 20 times minus cosecant theta cotangent theta, which makes it negative 20 cosecant theta cotangent theta d theta. So what is theta? Theta is 30 degrees or power 6. So minus 20 cosecant power 6, cotangent power 6. D theta is plus minus power 180. It has to be in radians. That's why I changed it. Now, cosecant power 6 is 1 over sine power 6, 1 over 1/2 or 2. Cotangent power 6, we know it to be square root of 3. If we don't know, we just reciprocate the tangent. And when we put them all together, this cancels this one, gives you 9. And we get, by the way, minus times plus minus still minus plus, or plus minus makes no difference. One is positive, one is negative. So plus minus 2 square root of 3 power 9. And this is exact class according to this calculation. So we keep it that way. You don't have to change the pi. Okay. Relative, so it's plus minus 1.21. Okay. But this is a better. It's always important that you show this value and then put it into a calculator, however many decimals they ask you. If they don't, you either keep that or you put many, many, many more decimals. What is a relative error? By definition is dx over x. So that means the amount of error over the actual amount. So dx, you can write this or write this. Either way makes no difference. Write any of it. And what is x? X is 20 times 2. The question is why? Because x is 20 cosecant theta. And cosecant of 30 degrees of power 6, we showed that it's 2, right? We showed this is 1 over 1/2 or 2, right? So 20 times 2. That's how we get that. X from here. Okay. And now everything cancels out except square root of 3 power 180. Don't forget the plus minus. Say these two cancel each other. 20 times 2 cancels out 20 times 2. So it's plus minus 0.03 or plus minus 3%. So we change it to a percentage. Normally we do that. Hyperbolic functions. Remember, unit circle are in the form of x squared plus y squared equals 1. And therefore cosine squared and sine squared, they add up to 1 in the case of a unit circle and trigonometric identities. In the case of a hyperbola, x squared minus y squared is equal to 1 is a hyperbola, and that gives rise to cos squared minus sinh squared equals 1. That's why it's related to that, and therefore that's why it's called hyperbolic functions. Now here's a definition you may remember from even pre-calculus. Cos x is e to the power of x plus e to the power minus x divided by 2. Sinh x is e to the power of x minus e to the power minus x divided by 2. These two are by definition. And then the rest of them are similarly defined as trigonometric identities. For example, here's the identities. Cos squared minus sinh squared equals 1. Okay. Hyperbolic cotangent squared minus 1 equals hyperbolic cosecant squared. X, 1 minus hyperbolic tangent squared equals to hyperbolic secant squared x. These are like Pythagorean identities. Cosine squared plus sine squared equals 1 and so forth. Sine 2x plus 2 sine x cosine x. So sinh 2x is 2 sinh x cos x. Cos 2x is cos squared plus sinh squared. In that case, cosine 2x plus cosine squared minus sine squared. So there are some differences and some similarities. So those are some of the identities, okay? The other identities, again, similar to trigonometric functions. Remember, tangent is the ratio of sine over cosine. So hyperbolic tangent is sinh over cos. Hyperbolic cotangent is cos over sinh or the reciprocal of that. Hyperbolic cosecant is 1 over sinh and hyperbolic secant is 1 over cos. So these are very similar to trigonometric functions and definitions and identities. As you recall, trigonometric functions, they are all odd functions except cosine. And you remember odd and even. F of minus x equals f of x becomes even. F of minus x equals minus f of x becomes odd. And in this case, it's similar situation, sinh and cosh. Sinh is an odd function, cosh is an even function. Also, we remember sine of alpha plus beta. Now, sinh of alpha plus beta, or x plus y, is sinh x cosh y plus cosh y sinh x. As you remember, sine of alpha plus beta was sine alpha cosine beta plus cosine alpha sine beta. So similar to that. Now, to take the derivative of sine was cosine. Now, the derivative of sinh is cosh. The derivative of cosine was negative sine, but in this case, the derivative of cosh is positive sinh. So these are some differences. The derivative of tangent was secant squared. In this case, the derivative of hyperbolic tangent is the hyperbolic secant squared x, and the rest follow. All right, we also have the inverse hyperbolic functions. So hyperbolic functions were defined as functions of exponential format. Now these are defined as functions of logarithmic format. It can be easily proved. I have in my lectures. And so, for example, the derivative of sine inverse was 1 over square root of 1 minus x squared and the rest of them. Now the derivative of sinh inverse is 1 over square root of x squared plus 1. It has some different, similarities. And again, all of them can be proved. Let's look at a couple of examples. For example, we said cosh squared minus sinh squared equals 1. We want to prove that. And the proof comes from the definition. We remember the definition of cosh and sinh. This is essential. We must really be very comfortable with the definition of a cosh and sinh, which means cosh is e to the power of x plus e to the power minus x over 2. Sinh is the same thing, but negative in between. E to the power of x minus e to the power minus x over 2. So to prove this is 1, we start with the left-hand side. LHS, left-hand side. Cosh squared minus sinh squared. And that means this one squared minus this one squared. And all we have to do, square it. Let's see what happens. First and foremost, each one has a denominator 2 squared or 4, so we have a common denominator, right, everybody? We have the common denominator 4. This is e to the power of 2x. Then 2 e to the power of x times e to the power minus x. Then this one to the second power is e to the power minus 2x. This is the same thing, but in between there is negative, okay? So minus 2 e to the power of x, e to the power minus x. So we have this. I hope everybody is okay with squaring each case. Now let's see what happens here. When we distribute the negative, everybody, so let me do that so you can see that. We change this to a plus, this becomes negative, this becomes positive, this becomes negative. So this one cancels out this one. This one cancels out this one. I hope you recognize this. as 1. So with this is 2. So is this one negative times negative 2. Remember it was negative here. Makes it positive 2. So you have 4 over 4 or 1. So I hope everybody's okay with this. Prove 1 minus hyperbolic tangent squared x equals hyperbolic secant squared x. Just as we did with Pythagorean identities. This we have already proved. We're going to start with that. And now since we want this to be 1, let's divide by this. Let's divide by cosh squared, everybody. It's very simple. So what happens? This one changes to 1. Sinh over cosh is hyperbolic tangent. So minus hyperbolic tangent squared. 1 over cosh is 1 over cosh is hyperbolic secant. So 1 over cosh squared is hyperbolic secant squared. So pretty straightforward, everybody. ddx of sinh 10x squared. Just the way we did trigonometric functions. I'm going to say sinh and I'm going to stop. The answer is cosh. But cosh of what? We need an argument which is the same argument 10x squared. And then the chain rule takes over. Now I need the derivative of 10x squared, which is 20x. And of course, we put it in front. So it's very straightforward, everybody. Let me just wait for everybody to catch up. Okay. All right. Cosh. The answer is sinh. We need the same argument. And now the derivative of that. Remember, square root of x is x to the power of 1/2. And its derivative is 1/2. X to the power of negative 1/2. Or 1 over 2 square root of x. So it's pretty straightforward, everybody. We put them together. Sin squared of x over 2 squared of x. Hyperbolic tangent of 1 plus e to the power of 2x. Hyperbolic tangent. So that makes it hyperbolic secant squared. Of the same thing, everybody. Let me use a different color. And now times the derivative of this expression. What is the derivative of 1 plus e to the power of 2x? Is e to the power of 2x times what? 2. And we put that in front. Looks like this. Can ignore. Looks like this as the final answer. Okay. So we put this in front. 2 e to the power of 2x. Hyperbolic secant squared 1 plus e to the power of 2x. So we put that in front. Y equals sin inverse of x squared. And I have the formulas for you here. So we're going to stick with this. If it's x 1 over square root of x squared plus 1, remember, if I change this to u, everybody, just as an example, u, then instead of x squared plus 1, I have u squared plus 1. Instead of 1, I have du dx. Therefore, I'm going to have 1 over something here. That means this one to the power of 2. And so x squared to the power of 2 or x to the power of 4. This is and then times the u dx, the derivative of x squared, which is 2x. Putting it together, we get this one. What about this one? We're going to do the same thing. What goes in here? Tan squared x. What goes in here? The derivative of tangent, du dx. I'm following this formula. Let me box that. This one. So tan gives us secant squared. Now this can be simplified. The numerator is secant squared. Tan squared plus 1. I hope you remember it was secant squared from Pythagorean identities. And so this doesn't come out as secant, but rather this comes out as absolute value of secant. Okay, remember that. So they cancel each other, but the absolute value sign remains. That's important. E to the power of x times cos x. We need a raised dot. To make sure everybody understands, we are dealing with the product rule. Fg. So f prime is e to the power of x times cos x plus this one, the derivative is sinh x times e to the power of x. So if I take this one out as a common factor, I get cos plus sinh. You may recognize that if you add these two cancel each other, you get e to the power of x and e to the power of x, 2 e to the power of x divided by 2, or e to the power of x. I hope you understand the sum of these two using this is e to the power of x. And e to the power of x times e to the power of x is e to the power of 2x.